Thanks for having me. I guess I was already sort of introduced, but this is my officially scheduled section. Oh, awesome. Thank you. We're getting kind of late, so this is the first segment sponsored by Red Bull.
Corey had one during his talk. He didn't dedicate it. Oh, right, yeah.
Yeah, Corey just drinks a Red Bull at 12:30 in the normal course of things. Okay, so as you can see, this is going to be an introduction to spectral graph theory. Spectral maybe makes us think of something like colors or rainbows. In some sense, a graph spectrum is like an array of different things that describe the graph, but it's not like explicitly colorful like this. What spectral graph theory really is some sort of way that you can understand graphs and their structure by the parameters associated with matrices that kind of encode the information of a graph. So if we want to get started with the first slide where we'll meet the first type of matrix we're going to be talking about. Okay, so for every graph, there's already been a graph theory section, right? So hopefully we all remember what a graph is. You've got some vertices, you've got some edges. Edges connect pairs of vertices. It's very natural to think about a graph as being a drawing, right? Where, for example, C4, the graph that we're going to start working on for this first example, we call it a cycle on 4 vertices because its drawing looks like this. So we've got 4 vertices, we've got 4 edges. They go in this circular type of fashion. But really, this is not the graph. This is a drawing of a graph. The graph is just the information about what's the vertex set, what's the edge set, and sort of how do the edges connect vertices. So there's multiple natural matrices that encode some or all of the same information as a picture of a graph. And the first one that we're going to dig into is called the adjacency matrix. So the adjacency matrix of a graph is if you have n vertices in your graph, the adjacency matrix will be an n by n matrix. And it's defined very simply. The ijth entry is 1 if vi vj is an edge. So we're always going to be labeling our vertex sets v1 through vn. And if vi vj is not an edge, then your ijth entry will be 0. Okay, so just to make sure we understand, here's my C4, the adjacency matrix of C4, which I'll always denote by A. I like to keep things straight in my head to actually sort of decorate adjacency matrices. So these are not part of my matrix. I'm just labeling my rows and columns to make sure I know which corresponds to which vertex. I'm always going to use the natural 1 through n order for both the rows and columns. Okay, so let's build the adjacency matrix of C4, and we'll see how it goes. So I need to, just for each entry, say, do the 2 vertices make an edge or not? The first thing that we can notice is we're only going to be working on simple graphs here. So we, in particular, will never have loops. And so on my diagonal, I'm always going to have zeros, right? A vertex is not in an edge with itself. For all of the off-diagonal pairs, well, let's just look. V1 is in an edge with V2. It's not in an edge with V3. It is in an edge with V4. So I get 0, 1, 0, 1 for my first row. Similarly, my second row, V2, V1 is an edge. V2, V3 is an edge. V2, V4 is not. 1, 0, 1, 0. And then actually, I mean, you can go through checking case by case, but I'll have a sort of nice symmetry in this adjacency matrix, where the first row and the third row are actually the same, and the second row and the fourth row are actually the same. Doesn't always happen like that. We will dig into some properties that all adjacency matrices have in a second. But maybe, I mean, if you sort of stare at this adjacency matrix for long enough, you can maybe even kind of see a way in which this sort of looks cyclic. Like here's the 2 neighbors, here's my 2 neighbors. They kind of, the pair of 1 sort of just shifts along with each row. Okay, so that's the idea. And this does store all the same information as this picture, right? We can go from one to the other and back. Turns out that using the tools of linear algebra on matrices like these, just the things like the eigenvalues and eigenvectors of the matrices will give us a lot of information about what the graph structure actually looks like. Okay, oh, and I think I say, what is the square of this adjacency matrix? Not necessarily clear why multiplying an adjacency matrix by itself would be interesting at all. It's, if you multiply the adjacency matrix by itself, it's not storing the same information about vertices and edges anymore. But we are going to come back to this. It turns out that there is interesting information captured by taking powers of adjacency matrices. So let me just do it for you quickly, and maybe it will stay mysterious for a few minutes. But hopefully you'll see that just like we see a lot of nice symmetry in the adjacency matrix, the square is also going to have nice symmetry. Okay, by the way, it's really good that Nicholas Van Essen is not in the audience anymore. He taught me linear algebra. He'd probably be ashamed by how much linear algebra I'm going to kind of take as prerequisite for this section. I'm going to imagine we all know how to multiply matrices. So what do? I take each row and dot it into each column. Zero, 1, and 1, and 1, and 1, so I'll get a 2 here. My second entry, 0 times 1, 1 times 0, 0 times 1, 1 times 0. My 1s sort of don't line up here, so this actually gives me a 0 entry here. For the third entry, my 1s line up again, so I'll get a 2. And my fourth entry, I'll get a 0. You don't need to watch me do this 16 times. One more time to see that something different will happen in the second row. Now I have 1 times 0 plus 0 times 1 plus 1 times 0 plus 0 times 1, so I get a 0 here first. And now the second entry of the second row, my 1s line up. So I'll get, it turns out, this pattern in my square. So definitely looks different from the ordinary adjacency matrix. For one thing, our ordinary adjacency matrix has all zeros on the diagonal. My diagonal here does not have zeros, but there still are obviously patterns that are happening in here. And we'll talk about how you can interpret the entries of this matrix in a few minutes. Okay, so with that introduction done, hopefully we all know what the adjacency matrix is and are ready to think about it. Let's go to the next slide and convince ourselves of a few basic facts about adjacency matrices. I think the very, very first class I ever took here at Montana, many moons ago, Brad might remember the exact date. I think it was fall of 2013. It was Mark Kyle's graph theory class, and he told us, when you're preparing your homework, show is synonymous with prove. So all of these are facts which will add to my QED count. Fact 1, adjacency matrices, always symmetric. So G, a graph. I want to show AG is symmetric. Well, one of several equivalent ways that I could explain what it means for a matrix to be symmetric would be to say that the ijth entry is equal to the jith entry for all I and j. But if you think about how an adjacency matrix is defined, this is almost immediate. So Aij is equal to 1 if and only if Vi, Vj is an edge of my graph. If and only if Vj, Vi is an edge of my graph, right? An edge just says two vertices are connected. There's not any sort of order to an edge. If you think about directed graphs, then this would not necessarily be true. But in normal graphs, if VI, VJ is an edge, VJ, VI is an edge, so AJI is also equal to 1. So AIJ is 1 if and only if AJI is 1. If it's not 1, it's 0, so they always agree. QED. 5. We'll get there. Second fact, entries of my adjacency matrix sum to 2 times the number of edges in my graph. This might sound familiar if you know about the handshaking lemma. So what I'm going to say here is the sum of my AIJ entries counts every edge of G exactly 2 times. Right? We just talked about the fact that the edge ij is the same as the edge ji. So once for aij and once for aji. So every time I see an edge, I see exactly 2 ones contributed to the sum. So when I add up all the ones in the sum, I'm going to get 2 times the total number of edges that contribute to it. QED. And finally, okay, I mentioned handshaking lemma. What do we know about 2 times the number of edges in the graph? That should be the same as the sum of my vertex degrees. And in fact, not only is that the case, but the adjacency matrix sort of sorts out where each vertex degree in that sum is very nicely. The ith row or ith column of my adjacency matrix has a row sum or column sum of exactly the degree of the vertex. So this is another way you could sort of prove the handshaking lemma, right? So here, I'm going to just, again, observe how the ones in the ith, say, row appear. In the ith row, aij is 1 if and only if vi, vj is an edge. So the number of ones in row I is the number of edges containing vi, which is just the degree of vi. QED, up to 7. Corey, you needed to just think of this strategy. It's not, it's a proposition, they're important facts. Okay. I promise it will get more interesting, but we want to start slow, right? We want to know some things that adjacency matrices do. As you're going to see, adjacency matrices have many more sort of deep properties that tell me more particular things about the structure of my graph. Let's start with this. We saw the adjacency matrix and its square, and you saw that the square of the adjacency matrix had nice structure, right? The square of the adjacency matrix is still symmetric. It seemed to not just be populated with random numbers. It turns out that in the square or the cube or any power of an adjacency matrix, all of the entries actually have a really particular interpretation. They're not anymore just telling you, is there an edge between 2 vertices, but they are telling you something really nice to know about the structure of your graph. They're describing how many ways you can use exactly k edges for the kth power to walk between vertex I and vertex j. So let's prove that if A sub g is my adjacency matrix of G, the ijth entry of the nth power, okay, n is usually number of vertices, but I chose n to just be a power here, is the number of length n walks from vi to vj. Okay, so claim in AG to the n for any ij that I choose, the ijth entry equals the number of length n walks from Vi to Vj. By the way, if you want a picture in your head, you don't remember what a walk in a graph is, I think about sort of walking along edges. So this is a sequence of n edges where every two adjacent edges in the sequence meet in a vertex. A walk is not necessarily like a path or a cycle. So it can do things like this and even repeat edges. It just has to be some sort of sequence of edges in my graph that I can continuously walk along. There should be n total edges in this sequence. The first edge needs to sort of start at Vi and the last edge needs to end at Vj. Okay, so that seems like a jump up in difficulty, right? From basically proving the handshaking lemma. But this actually, if you know the right proof, is a statement that I can also convince you of fairly fast. We're going to use everybody's favorite, induction, on the power of my matrix. The base case here, I'm going to say is raising to the first power. If you want to say that the 0th power is the identity matrix, I guess it's true that there's one length 0 walk from a vertex to itself and 0 length 0 walks from a vertex to any other vertex. But the sort of first interesting case is raising to the first power. So is it true that the ijth entry of the adjacency matrix tells me the number of length 1 walks between any two vertices? Even a non-graph theorist is nodding. It does have this property. Vi, Vj have at most one length 1 walk between. A length 1 walk from Vi to Vj is just an edge that starts at Vi and ends at Vj. There's 0 if Vi Vj is not an edge of G. So okay, base case done. Because a length 1 walk between two vertices is the same as just an edge between two vertices. So the interesting thing is the inductive step. So let me fix n bigger than 1 and say a g to the n minus 1 has the right property. What I'm going to do is write ag to the n in a way where I'll be set up to use my inductive hypothesis. What do we think would be a nice way to write ag to the n? If I know about its n minus first power? Yeah, exactly. I want to somehow force this to have an a to the n minus 1 in it. Matrix multiplication basically, I mean, it does and doesn't work like multiplying real numbers. There's some things, of course, that matrix multiplication doesn't share with multiplication of real numbers, but we can write like this, just like you'd write x to the n is x times x to the n minus 1. Okay, perfect. And now let's think about how matrix multiplication works. And writing ag to the n like this, what is the ijth entry of ag to the n? Okay. So to get my ijth entry, I take, what was I doing when I was going like this? I was taking my ith row of my matrix on the left and dotting it into the jth column of the matrix on the right. When I do that, so I'm going to get a sum. All the things in my sum look like something that came from the ith row of AG. And then it's multiplied by, I'll call the entries of my power A hats. And so this is from the jth column of AG to the n minus 1. And I'm doing a sum here from k equals 1 up to number of vertices. N is a power of a matrix, so the number of vertices will be an indeterminate letter. And somehow we want to say that this sum does actually represent exactly the number of walks on n edges exactly between vi and vj. Well, by induction, I know something about sort of 1/2 of each product that I'm adding up. A hat kj is the number of length n minus 1 walks, not from vi to vj, but from whatever vk this subscript matches to vj. Okay, so I have a vk here. Here's my vj. There's some number of ways. It could be 0, or it could be a lot, but there's some number of walks of length n minus 1 from vk to vj. And the idea here is that I can build a length n walk from vi to vj by saying, okay, a length n walk from vi to vj first goes from vi to some other vertex. And then I choose from this second vertex on my walk any length n minus 1 walk to get me to the ending point that I want. And remember that this aik is 1 if and only if vi vk is an edge. So if I can make a walk that goes from vi to vk and then takes n minus 1 more steps to go to vj, this term in my sum tells me exactly how many such walks I can make. If vi vk is not an edge, then there are no such walks, and this term in my sum is 0 times something. Okay, so the upshot of what I just said is aij times a hat, aik times a hat kj is the number of length n walks that go vi to vk and then eventually end in vj. So every length n walk from vi to vj looks like exactly one type of walk like that. So I just add up the number of all types of walks with second vertex vk, and that gives me my total number of walks. 8. Okay, so maybe we can put up the whole slide for a second, because I know that this one's kind of full. So spectral graph theory, like I said, is going to kind of dig into what things like the adjacency matrix of a graph can tell me about the graph. We already hopefully are starting to believe that the adjacency matrix does encode more information than just what the vertices and edges of my graph are. If I want to translate back into a picture, I can look at things associated with the adjacency matrix and just from these matrices figure out things about my graph. The main thing that spectral graph theory focuses on are actually the eigenvectors and eigenvalues associated with the adjacency matrix, as well as other matrices, which you can kind of naturally define to talk about how graphs look. So we want to know what eigenvalues and eigenvectors are. An eigenvector is just a non-zero vector where when you multiply it by a matrix, you just get some scalar multiple of your vector back. And the scalar multiple of your vector that you get back is the associated eigenvalue of that vector. So remember, we talked about C4 having that adjacency matrix that we computed. Let's figure out what the eigenvalues and eigenvectors, well, we'll get the eigenvectors as we find the eigenvalues, are for the adjacency matrix of C4. Okay. By the way, I mean, here's the first place where I'm going to start not doing as thorough a job with the linear algebra as I could. There's many, or at least several ways that you could think about getting eigenvalues and eigenvectors. Thinking about things like characteristic polynomials in general for spectral graph theory, very, very interesting. We're not going to linger on it. I'm just going to find these eigenvalues by hand. My matrix, if you'll remember, looked like this. And now, what would it look like if I had an eigenvector? I have some vector with components v1, v2, v3, v4. I multiply it by this matrix, and it just turns into itself times lambda for some lambda. So one way that you can, by hand, figure out what the eigenvalues and eigenvectors of a matrix are is just say, okay, this is secretly going to give me like a system of equations. So let's multiply it out and see what we get. If I do this, this is really the vector v2 plus v4, v1 plus v3, v2 plus v4, v1 plus v3, if I multiply that matrix and that vector together. So I know that v2 plus v4 is equal to lambda v1, v1 plus v3 is equal to lambda v2, v2 plus v4 is equal to lambda v3, and v1 plus v3 is equal to lambda v4. Okay, so now I can say some things. If lambda is not equal to 0, then I could sort of divide everything in this whole system of equations by lambda. And in particular, I would know that v1 is equal to the same thing as v3, and v2 is equal to the same thing as v4. So if lambda is not equal to 0, then v1 equals v3, and v2 equals v4. Okay, but that's nice, because then I can replace every v3 and v4 that I see here with a v1 and a v2. So really, this reduces to v2 plus v2 is lambda v1, 2v2 is lambda v1, and v1 plus v1 is lambda v2, 2v1 is lambda v2. So v1 is lambda over 2v2, v2 is lambda over 2v1. This implies v1 is lambda over 2 times lambda over 2v1, lambda over 2 squared v1. So lambda over 2 squared is 1. Lambda over 2 squared equals 1. So lambda is plus or minus 2. By the way, we could figure out what the eigenvectors here are. if lambda is 2, then 2v1 equals v2, 2v2 equals 2v1. v2 and v1 are both equal, so v2, v1, v3, and v4 are all equal. Maybe I'll write it like this. My vector looks like t for some number t. This brings up a fact about eigenvectors, which if you've taken a linear algebra class, you'll know. If you have an eigenvector, then any scalar multiple is also an eigenvector with the same eigenvalue. So I could actually just choose any value of t here that I wanted to be standard. Let's say 1, 1, 1, 1 would be the most sort of normal looking eigenvector. Although maybe you would actually arguably want like 1 half, 1 half, 1 half, 1 half if you want a normal eigenvector. Okay, anyway, so we can dig out what the eigenvector associated here is. There's up to scalar multiple only one choice. And similarly, for my eigenvalue of -2, I can dig out up to scalar multiplication a unique eigenvector. On the other hand, if lambda is equal to 0, so I can't just divide everything here by lambda, that does tell me v2 plus v4 equals 0 and v1 plus v3 equals 0, plugging 0 into all these equations. So I know that my eigenvector would look like v1 is some s, v2 is some t, then v3 is -s, and v4 is -t. And unlike in the first two cases we talked about, there's more than just the scalar multiple choice of what this vector looks like. I can actually make two linearly independent eigenvectors with the same eigenvalue. For example, I can choose s equals 1 and t equals 0, or I could choose s equals 0 and t equals 1. Those are not scalar multiples of each other. So this is an example of having what we call an eigenvalue with multiplicity. The multiplicity of 0 as an eigenvalue is 2 because I can find two linearly independent eigenvectors with the same eigenvalue. And we're always, for all of the statements that we talk about today, including eigenvalues, we're always going to think about eigenvalues counted with multiplicity. So I'm going to say the eigenvalues here are -2, 0, 0 again, and 2. You'll notice this was a 4x4 matrix, and I have 4 real numbers with this multiplicity factored in as eigenvalues. And here's another thing that I'm going to not justify. It takes work to show, but there is this real spectral theorem, which says if you have a real symmetric matrix, then you're always going to get not just n eigenvalues of multiplicity, but you actually get n linearly independent eigenvectors to go with those eigenvalues. And in fact, you can assume that those eigenvalues make an orthonormal basis if you want.
And are they always going to be real?
They will always be real if it's a real valued matrix, yes. Okay, I don't know if that's a QED, it's more of an example. But we can figure out these eigenvalues. Oh, and then by the way, I say, what about its square? In the interest of time, I'm not going to go through showing this, although I guess it would give me another QED. Because a squared also has dimension n, it's going to have, n eigenvectors. So if I can show you n eigenvectors and tell you the associated eigenvalues, then those are all of the eigenvectors that it has. And it's not hard to see that if v is an eigenvector of a with eigenvalue lambda, then v is an eigenvector of a squared with eigenvalue lambda squared. So with multiplicity, the eigenvalues of the square of this adjacency matrix are going to be negative 2 squared is 4, 0, 0, and 4. Okay. Okay, cool. We'll say 1 QED for that verbal proof. So let's use another nice fact about how eigenvalues work to prove our first statement relating the eigenvalues of a matrix, an adjacency matrix, to some piece of information about the graph. The basic idea here is you could take this sort of partial information. I can just tell you, I don't tell you the full structure of G, I just tell you what the eigenvalues of this adjacency matrix are, and somehow from those eigenvalues you can figure things out about the structure of G. So here we're going to figure out the first thing that eigenvalues say about the structure of G. The trace of a matrix is just the sum of the entries on its diagonal, and it's an eigenvalue fact that the trace of a matrix is always equal to the sum of the eigenvalues. Doesn't necessarily mean that the entries on the matrix's diagonal are just the eigenvalues, but they add up to the same thing as adding up all the eigenvalues. Okay, so if I have adjacency matrix G, this problem has two things to show. Ooh. The trace of the square of the adjacency matrix, which I could express using this fact as the sum of the squares of the eigenvalues, gives me twice the number of edges. And the trace of the cube of the adjacency matrix, which I could express as the sum of the cubes of the eigenvalues, gives 6 times the number of triangles in G. Okay, let's prove. So for first part, the trace of AG squared by that fact, it is equal to this sum. And so I want to relate this trace to the number of edges in G. Well, by definition, if A squared has entries A hat ij, I'm just summing up these diagonal entries. And by that last theorem we proved, I'm really adding up the number of length 2 walks from a vertex to itself. Okay, if I'm going to have a walk using exactly 2 edges from a vertex to itself, I'm also going to be in graphs here that don't have multiple edges. So here's Vi. I can take one edge to go to Vj. Now to get back to Vi, I have to do a silly sort of walk thing where I repeat an edge, right? I can't go from Vj anywhere else. So I just have to come back along this same edge. So this is just the number of edges containing Vi. Every Vi walk of length 2 looks like take an edge that contains Vi and then take that same edge a second time. So the number of choices that I have for that edge is just the degree of Vi. So this tells me that this sum of lambda I squareds is equal to the sum of the degrees in my graph, which by the handshaking lemma is 2 times the number of edges. So actually, yes, if I have the full adjacency matrix, I can add up all of its entries and figure out the number of edges in my graph, but I don't need all that information. If I tell you just the spectrum is what we call this list of eigenvalues, you can just square all those eigenvalues to find what the trace of the square of the matrix would be, add them together, and you get twice the number of edges. So it's like magic, right? You have this much sort of smaller set of information than the full structure of your graph, and yet you can really directly infer this property. Okay, so that's the first QED. Second part, by the way, I don't know if any of my graph theory students are watching. It's, start of spring break for them, so probably they're all off in Cancun or somewhere, but this was a homework question that I assigned them a few weeks ago. We can do something really similar to figure out something about walks of length 3 in a graph and the number of triangles. So the trace of the cube of my adjacency matrix is supposed to be saying something about how many triangles I have. So I'm going to sort of start in the same way. By this fact, it is equal to the sum of these cubes of eigenvalues. It's also equal to, using that theorem, the sum from I equals 1 to n of the number of length 3 walks from VI to itself. Again, let's just think about what a length 3 walk from VI to itself looks like. So I start here at VI. I go to some vertex VJ. I go to a vertex VK, which is different from VI. In theory, I could walk back to VI for my second edge, but then I have to walk away from VI for my third edge if I do that. So VK actually also can't be equal to VI. So I walk from VI to VJ to some different VK, and then back to VI. So the only length 3 walk from a vertex to itself looks like a triangle. So all of these length 3 walks from a vertex to itself look like triangles. You might then think that the number of walks of length 3 from a vertex to itself are the number of triangles that contain the vertex. That's almost right, but does anyone see what the problem is?
Double counting.
Yeah. So if I have a triangle here that doesn't just make one length 3 walk from V to itself, because in a walk, like the order that I take the edges matters. So I could go forwards, quote unquote, around this triangle, VI to VJ to VK to VI, or I could go backwards, VI to VK to VJ to VI. So by this double counting, this number of walks is 2 times the number of triangles containing VI. Okay, and now we're almost done. So I know that the sum of the cubes of my eigenvalues is the sum from I equals 1 to n of 2 times triangles containing VI. I can factor that 2 out. And then I have the sum of triangles containing VI over all the vertices in my graph. Well, by something very similar to the handshaking lemma. Every triangle has 3 vertices, so every triangle is triple counted by that sum. So this is really 2 times 3 times number of triangles in G. 11. Okay, let's see, what's next? Oh yeah, okay, first lengthier thing. Let me keep an eye on the time. What am I supposed to be going to now? 10? A little bit after. I'll try to be fast and wrap up by 10. If I can't, I'm sure it's okay. So this next question, we're going to be focusing just on one eigenvalue of my adjacency matrix, specifically the biggest. I haven't told you that there's multiplicity 1 on the biggest eigenvalue, but you make the list and circle a biggest number in that list. There's some really nice connections between what the average and maximum degree in the graph are and this biggest eigenvalue. In some sense, we think of the biggest eigenvalue as telling us something about degrees in my graph. Specifically, if my biggest eigenvalue is lambda n, then lambda n is bounded between the average and maximum degrees in my graph. So let's see. I decided that I was going to do this with every page that I got through because I didn't staple them, and so if they get out of order, it's going to be impossible. This is the first one where I might need to refer to some notes. We'll see how it goes. Okay, so I won't count this as 2 QEDs because it is stated as one theorem, but I'm going to prove it in 2 parts. All right, I have sort of 2 inequalities that I want to show, and I'm going to break them up separately. So the first thing I'm going to do is show that my biggest eigenvalue is less than or equal to my maximum degree. And actually, I'll show something slightly stronger. I'll show that for any eigenvalue lambda, the absolute value of lambda is less than or equal to maximum degree. So as we saw in our example with C4, eigenvalues definitely can be negative. So this is actually a little bit stronger. It says not only is the biggest positive eigenvalue less than or equal to max degree, the biggest negative eigenvalue can't exceed negative delta. Okay, so how am I going to do that? Right. Let x be an associated eigenvector. I should probably put arrows or something on my x's. I know some people don't. With eigenvalue lambda n, or lambda. And I want to conclude something about the absolute value of lambda here. So what I do is let x sub j be a component of x with biggest absolute value. So absolute value of x sub j is at least absolute value of x sub I, all I. By the way, remember we said eigenvectors are non-zero, so this is strictly bigger than 0 because I've taken an absolute value. I can't have just 0, 0, 0, 0, 0. There's some non-zero entry, and then its absolute value is strictly bigger than 0. Okay, so what I'm going to do is think about the jth entry of my vector. Okay, I know that my adjacency matrix times x gives me lambda times x. So lambda times xj, what's the jth entry of this thing? I take the jth row of my adjacency matrix and dot it into x. So this is a sub ji times xi, I going from 1 to n. Okay, and now we get to use the triangle inequality, everybody's favorite inequality. The absolute value of lambda times xj, absolute value breaks up over products. This is the absolute value of this sum, a ji x I. Triangle inequality, absolute value of a sum is less than or equal to the sum of the absolute values. right? We probably are used to triangle inequality for 2 terms, but you can state it for any number of n terms. So this is less than or equal to the sum of the absolute value of AJI times the absolute value of XI. And now we get to do some fun estimation. Okay, absolute value of Xi, I'm going for an upper bound here, so what could I replace that with that should be relevant and at least as big as the absolute value of Xi? Certainly I could. I don't know if I know things about the value of Xi squared. What I'd like to do actually is, this product is a little bit hard to parse. I would love it if I could kind of move half of this product out as just like a multiplicative factor on this sum. Something associated with, so there's one thing I know about the absolute value of Xi. Yeah, Xj is the biggest. So I can just put in Xj for everything. Yeah, perfect. So I definitely want to sort of cast around for things that I know I can get an inequality on for Xi, and I'd like them to just be numbers. So this is less than or equal to just taking the absolute value of all these AJIs and multiplying them by the absolute value of Xj, because that's the biggest one. And now this is a sum indexed over I, not j, so I can take that Xj and pull it out. So here I just get the absolute value of Xj times all these AJI entries. I can drop the absolute value there because my adjacency matrix is 0, 1 valued. And we saw in that first QED, facts about adjacency matrices. If I take the row or column sum, I just get the degree of the relevant vertex. So this is the sum of the entries in the jth row, so it gives me the degree of Vj. Okay, so I conclude that absolute value of lambda times absolute value of xj is less than or equal to the absolute value of xj times the degree of Vj. And in particular, we noted that this absolute value is strictly bigger than 0 of xj. So I can cancel absolute value of xj off from both sides of that inequality. And actually, this tells me something slightly stronger than that the absolute value of lambda is at most the max degree. The absolute value of lambda is at most the degree of this specific vertex I've chosen, but as a sensible upper bound. Certainly that's not bigger than the biggest degree in my whole graph. And it could be equal to the biggest degree in my whole graph. Okay, so that's the first half. Yeah, I know that this is longer. Okay, so we want to count that as a QED. Okay. Second half, we want to show that there's also a natural lower bound on my biggest eigenvalue. So the average degree in my graph is what you think it is. You take all of your degrees, you add them up, and you divide by the number of vertices you have. I'm going to say that D is my average degree here, and I want to show that that's less than or equal to my biggest eigenvalue. Okay, again, make sure I remember how to start here. Yeah, so this is another place where I'm going to mention a fact that I'm not proving from linear algebra. Since A is a real symmetric matrix, we may assume its eigenvectors form what we call an orthonormal basis. Of Rn. So A is an n by n matrix. not only does it have n linearly independent eigenvectors, but you can show that actually if A is real symmetric, then all of its eigenvectors are orthogonal. So when you take their dot product of two distinct ones, you get 0. And once you have an orthogonal basis, then you can easily make an orthonormal basis by just dividing each vector by its norm. Because as we discussed, if you have an eigenvector, then every scalar multiple of that is also an eigenvector, as long as you don't multiply by 0. Okay, so it's going to be important that we have this orthonormal basis because basically I'm going to make another sort of sum that I try to estimate, and this sum is going to involve a bunch of different eigenvectors getting dotted together, and it's really going to save my life that usually when I dot two different eigenvectors together, I just get 0. Okay, so let's say this basis is beta x1, x2 through xn are my vectors. And their associated eigenvalues are lambda 1 through lambda n. Okay, so what I want to do is then say, since beta is a basis, there exist real numbers alpha I such that, well, it's a basis for Rn, so I can make a linear combination of my basis vectors that makes any vector in Rn that I want. And I'm going to pick a very nice vector, the all ones vector, which I'll denote like that. Okay, so why is that useful? Because I can now do this. I'm going to make a vector D, which I get by taking my adjacency matrix and multiplying by this all ones vector. Okay, so on the one hand, I can figure out directly what this is, and I've called this vector D because this vector basically stores degrees, right? To figure out the ith entry of this vector, I take the ith row and dot it with the all ones vector. That's the same as just adding up all of the numbers in the ith row, and that's just the degree of the ith vertex. Okay, so A times the ones vector gives me this vector that stores all of my degrees. But on the other hand, and then what I want to do is say, I can dot this vector again with the all ones vector and just add up all the degrees in my graph. Okay, so in one sense, I can interpret this product as my degree sum. In another sense, I'm going to use the fact that this product, I can write it as a more complicated product involving a bunch of my different orthonormal basis vectors and try to get some other kind of expression that is going to be equal to this degree sum. Okay, so on the other hand, beta is an orthonormal basis. What I'm really doing here is multiplying by this combination of basis vectors. And each of these guys is an eigenvector of A, right? So multiplying matrix across sum of vectors works like you think it should. So here, I'm going to get the product of these AI xi transposes, or the sum times, okay, what happens when I hit each of these terms in this sum with my AG? I've got some alpha I times AG times xi. So I get the sum alpha I lambda n xi. Actually, how about well, at least explicitly write where these sums are going. Okay, now how do I multiply two sums together? In some sense, you could say, okay, I'm going to FOIL this out. Every index I and j here that I can pick, I get the product of two things. But in a very lovely way that things work in algebra, almost always when I take a product of something here and a product of something here, I'm going to have an xj times an xi where j and I are not equal, and that's 0 because all of these vectors are pairwise orthogonal. So actually, when I do this, the only terms that live are where I chose the same index from this sum and that sum. And in that case, what I get is alpha I squared lambda n xi transpose times xi. Xi transpose times xi, we can also simplify in a nice way. These are normal vectors. So if I dot a normal vector with itself, I get the square of its norm, which is just 1. So actually, this is lambda n times the sum of these alpha I squareds. The last thing I would like to do is figure out what the sum of those alpha I squareds are. And I do actually know something about that. If I take the all ones vector and I dot it with itself, I get this thing, right? Which we just said is the sum of these alpha I squareds. But this is also just equal to, I have n ones that I'm multiplying by n ones and adding all together. So this is just n. So I get n times lambda n is equal to this degree sum. And right. My inequality comes from the fact that oh, I'm sorry. This wasn't always a lambda n. This was a lambda I. Yeah, sorry about that. But I can replace it with a lambda n as an upper bound. So it is an inequality. I have this is at least my degree sum. So if I divide both sides by n, I get biggest eigenvalue is at least the average degree. OK, so QED again. And we're probably starting to feel like eigenvalues are pretty magical. This next problem, I'm really not going to call this QED because I'm not going to actually go through all of the work to demonstrate the claim that I make. But this next problem is intended to maybe indicate some of the limitations that analyzing a graph by its spectrum comes with. At this point, maybe you're thinking, okay, you were able to do basically hand-waved linear algebra magic and figure out a lot of different things based on just knowing these eigenvalues. Can you always just like reconstruct what a graph is based on only the eigenvalues of its adjacency matrix? If that's the case, then like we should probably stop graph theory because it's all just kind of linear algebra. But you won't be surprised to hear that this is partial information about a graph, and just knowing the spectrum of a graph does not tell you everything you want to know about it. So as an example here, I'm going to tell you that G is a graph. Its adjacency matrix has these eigenvalues for multiplicity. So a G has eigenvalues, looks similar to the ones that we found for C4, but there is an extra 0 there. What can we figure out about the structure of G and what can't we? So by the previous facts that we proved about how traces of powers work, I do know the number of edges in my graph. The trace was supposed to be 2 times the number of edges, the trace of the square. So I can figure out the trace of the square just by looking at the eigenvalues, right? The eigenvalues of the square are the squares of the eigenvalues here. And I just add them together to get the trace. So I have -2 squared plus 0 squared plus 0 squared plus 0 squared plus 2 squared over 2. This gives me 4, so my graph has 4 edges. The number of triangles in G. Well, 6 times the number of triangles in G was the trace of A cubed, so the number of triangles in G is the trace of A cubed over 6. So here I get -2 cubed plus 0 plus 0 plus 0 plus 2 cubed over 6. My numerator, when I cube 2 and -2, they cancel out, so I have no triangles. So this is a triangle-free graph. It has 4 edges. I know also that it has 5 vertices because an n-vertex graph gives me a spectrum of size n. But there are more than one 5-vertex graph with no triangles and 4 edges. So I can narrow down if I say what possibilities do I have based on the things that I know how to read off from my spectrum for G. I could have that picture, or I could have a connected graph, in which case it would be a tree or a star. Or maybe there's 4 possibilities. Sorry. Okay. Now, the fact that these graphs agree on these few dimensions doesn't necessarily mean they all have the same spectrum. Actually, some of these graphs do not have the spectrum -2, 0, 0, 0, 2. But if you actually go through and compute the spectrum for each graph, these 2 graphs are what we call cospectral for the adjacency matrix. So every matrix associated with the graph has some things that its spectrum can't detect. The adjacency matrix, we've just seen, cannot detect whether a graph is connected. Here's one disconnected graph and one connected graph that have exactly the same spectrum. So you're never going to be able to look at the spectrum of a graph alone and for the adjacency matrix and say, is this graph connected or not? So
those 2 graphs you have there that are co-spectral, they're seems to be a very nice, almost duality relationship between them. Is that a coincidence, or is that something you see a lot?
That's a good question. So I'm not an expert on cospectral pairs. I do know people who study this a lot. There's still lots of open research questions about when graphs can be cospectral. It is possible, like I said, for all of the sort of standard graph matrices to find cospectral pairs, but it's not necessarily easy to classify when two graphs will be cospectral for a certain matrix. So actually, in an REU that I participated in as a mentor last summer, one of the groups were thinking about ways to construct cospectral graphs for certain types of matrix. And I think that typically, like the fact that two graphs are cospectral, there should be some structural like implications, but
Okay, thank you.
yeah.
Can I ask a follow-up that piqued my interest here? You said cospectral pair of graphs, but could you have like 100 graphs of the same?
Yeah, I think it's not necessarily just two.
Right, okay. I mean, here maybe there's not a lot.
Yes, probably. I think that these are the only two out of this list of four. But in general, I don't think there's a guarantee that there's at most two graphs that share a spectrum. You just sort of find two and you say, okay, they agree. Okay, so with that said, I'll clean it up after. I need to stay organized. Last time I did this, I had all this paper, it all got jumbled up, and then I was like, I'm sorry, I can't even find the problem I'm working on.
I think leave them there till the end. It adds to the aesthetic.
Okay, I'm gonna chug some of this. Working on it. I think the main charm of this is like getting ever more delirious as we go on towards the end, right? So what we're going to do for the second half is now switch to thinking about a different matrix, which again has sort of different strengths and weaknesses. If there's any spectral graph theorists in the chat, you can fact check me on what the Laplacian can and can't do. If I remember, there's cospectral pairs of Laplacian where they don't agree on bipartiteness, but maybe that's a different graph, maybe a different matrix. Anyway, there's, like with the cospectral pairs we saw, there's some things that the Laplacian won't detect, but the Laplacian, slightly more complicated definition of matrix, is really good at detecting other things, including some things like connectivity that the adjacency matrix doesn't do well. So let's again just start with C4 as an example and write out what the Laplacian does. So the Laplacian matrix of a graph has three options now for how you figure out entries. It's not anymore going to have a zero diagonal. The diagonal entries are going to tell you the degree of each vertex. And then this version of Laplacian, there's also a signed Laplacian where you erase the negative ones. But this version of Laplacian will have negative ones in the off-diagonal entries corresponding to edges of the graph, and we'll still have zeros corresponding to non-edges. Okay, so let's...
Interrupt you here, actually. Where did this like come from, right? I mean, it's useful. It has properties. Do you know, like, is there some analog somewhere else? I mean, this term Laplacian.
Yeah, I know. As I've been preparing this, I'm still slightly stymied as to how people. Like, as soon as you start studying Laplacian, it becomes clear there's things that it does really nicely. Like, it's very nice, for instance, that the row and column sums all now are zero in the Laplacian. I'm not. I only pretend to be a spectral graph theorist. I'm mostly an extremal graph theorist. So I'm not the best person to ask on, like,
maybe the perfect person to ask, because you could tell me from, you know, the angle I'm looking at. But we'll learn some lovely things the Laplacian does. So hopefully, if that looked like a slightly unmotivated definition to you, there's a couple of things you could notice. Like, the Laplacian is not as weird as it seems. You can say the Laplacian is the difference of a diagonal degree matrix and the adjacency matrix. So it is built using two very natural matrices. And as we'll see in the next hour and a half, 2 hours, depending on exactly what the timing is supposed to be. Just tell me when I'm supposed to finish, and I'll stop. It can do a lot of really beautiful things. So C4, again, V1, V2, V3, and V4. V1, V2, V3, V4. 1, 2, 3, 4. So now what do I do? All of my diagonal entries tell me the degree of each vertex. This is a 2 regular graph, so I see 2s everywhere. And now I kind of have the opposite of the entries that I saw on the off diagonal in the adjacency matrix. So I get -1s where I used to see 1s. And where I saw 0s, I still see 0s. Okay, so hopefully seeing me write it down, we can keep in our mind the way that these are defined. I know that, well, at least to me, the first time I saw Laplacian definition, I was like, oh my God, this is so much harder than an adjacency matrix. Once you do a couple examples, you're like, you can remember the 3 things now. Okay, let's show something about the Laplacian matrix. I'm going to scamper lightly over the first part. Similar to adjacency matrices, these are real symmetric matrices, right? So in some sense, if you believe me that there's real eigenvalues for a real symmetric matrix, you can just say, okay, there's going to be real eigenvalues here too. But actually, we can say something stronger about the eigenvalues of the Laplacian. They're not even negative. We saw there's plenty of adjacency matrices with negative eigenvalues. Laplacian, all of the eigenvalues are 0 or strictly positive. Okay, so let's show that. Da, 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 da. And I'm going to introduce another important term from linear algebra. An n by n matrix M is called positive semi-definite. If x transpose mx is non-negative, for any vector x in the reals that I choose. So if I take x transpose mx, we've seen that that does just give me a number. And no matter what real valued vector I choose, I will get a non-negative number out of this. Positive semi-definite matrices have lots of nice properties. So basically what we're going to show here is that the Laplacian is positive semi-definite, and then it will follow almost immediately that it has non-negative eigenvalues. Okay. Let's show LG is positive semi-definite. To do so, I'm actually going to define a slightly different matrix, which is kind of going to be, it turns out, like small part of the Laplacian corresponding to just a single edge of G. So for an edge, Vi, Vj, Lvi, Vj is, let me make sure I say it right, it has, I'll say, I don't know, KL entry. 1 if K equals L and K is one of the indices I and J that actually correspond to these endpoints. It's going to have entry -1 if K equals I L equals J or vice versa. And it'll have 0 otherwise. So there's actually almost no non-zero entries in this matrix. It just adds a 1 on the diagonal for the ith and jth diagonal spots, and it adds a -1 in the places where the edge vi, vj sort of naturally shows up. Da, 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 da. Observe. LG is the same as taking the sum of these vi, vj matrices over all edges. Why? Well, let's just think about where entries in this matrix sum actually come from. So the KL entry here is, there's some different cases. If K equals L, so it's a diagonal entry, I get a contribution of 1 to that entry every time I see an edge that includes that vertex as an endpoint. So that's nothing more than the degree of that vertex. If K is not equal to L, then the entry is either -1 or 0. It only shows up in, at most one matrix, non-zero, the matrix corresponding to the edge between VK and VL, if that edge is present. If not, then in every single one of these matrices I add up, that's a 0 entry. So if VK, VL is an edge. Okay, so it's actually nice to, even though it looks more complicated to define it this way, it's nice to write the Laplacian as this sum of smaller matrices. And the way that we're going to do it is note for any real valued vector x, instead of thinking about taking x transpose L of gx all at once, I'm going to think about taking x transpose L vivj x for each of these edge matrices sort of one at a time. So what happens if I just take one of these products? Well, like we said, mostly when I multiply things in the vi, vj matrix by things in x, I'm going to get zeros because there's like 4 non-zero entries in this matrix. So if I think about taking L vi, vj times x first, almost all entries are 0. The ith entry, okay, for the ith row of this edge matrix, I'll see a 1 in spot I and a -1 in spot j. So I get xi minus xj. And the jth entry, it swaps. I get the jth coordinate minus the ith coordinate. So if I then multiply the result of that by x transpose, when I dot x transpose with the vector with this description, I'll mostly be adding up zeros. But the ith entry of x transpose is multiplied by xi minus xj. So I get xi minus xj. And the jth entry should be xj xi minus xj minus xi. This gives me xi squared minus 2xi xj plus xj squared. Anybody see a nicer way to write that? Yeah, it's a difference. It's a square of a difference. So this is xi minus xj quantity squared. Relevant thing is that a square is always bigger than or equal to 0. So if I then multiply x and x transpose on either side of the big Laplacian, I can say that this is really that sum. So this is over vi, vj, and edge, xi minus xj squared, bigger than or equal to 0. So check mark, the Laplacian is positive semi-definite. This problem did not say show that the Laplacian is positive semi-definite. It says show that it has non-negative eigenvalues, so I don't have my QED quite yet, but I have the main part of my QED. It's like one line to go from this to non-negative.
I feel like we've given out some checks for one-line proofs.
Okay, so now that we know positive semi-definite matrix, say x is an eigenvector with eigenvalue lambda. Positive semi-definite tells me I get that. But this, as always, I can associate matrix multiplication any way I want. This is an eigenvector, so this just gives me lambda x. So x transpose lambda x. I can factor a scalar out, lambda x transpose x. X transpose times x, as we mentioned, that gives me norm squared, right? In particular, this is bigger than 0. So I can divide it off, and I get that 0 is less than or equal to lambda. QED. Okay. We can say more than that these eigenvalues are all strictly positive. Again, we were able to say a surprising amount of stuff about the eigenvalues of a adjacency matrix. So let's see, adjacency matrices fell down on the job when it comes to determining connectivity. Laplacian matrices will not. In fact, you can read off really explicitly from the eigenvalues of a Laplacian matrix. We're not going to go through the full argument, but the argument here will probably indicate to you a stronger fact that you could prove. The smallest eigenvalue of any Laplacian is 0. That will also come up in a later proof, so let's keep it in mind. But the second smallest eigenvalue tells us, is my graph connected or not? If the second smallest eigenvalue is also 0, so 0 has multiplicity at least 2, then your graph is disconnected. If the second smallest eigenvalue is strictly positive, then your graph is connected. I think we've just written this if G is, so yeah, we're just showing if G is connected, then the second smallest eigenvalue is strictly positive. I think, yeah. So I think even as we go through the proof, hopefully at the end we'll be like, oh yeah, if it has multiple components, I could find different eigenvectors, like linearly independent eigenvectors that should give eigenvalue 0. Okay. So I want to say if G is connected, my second smallest eigenvector is not 0, but let's first note that lambda 1 actually will always be 0. Okay, first thing to observe is just, well, if I can find an eigenvector with eigenvalue 0, then I'm done. Then I have 0 as an eigenvalue with multiplicity at least 1, and because we've shown that all of these eigenvalues are non-negative, the smallest possible eigenvalue I could have is 0. So if I can show that 0 is always an eigenvalue, it must always be the smallest eigenvalue. Okay, and I claim that just taking the all ones vector multiplied by my Laplacian will indeed to give me 0. Well, what do I have in the ith row of a Laplacian? The diagonal entry is the degree of vi. I subtract a 1 for every edge that contains vi. So of course, those are exactly the same number. So the all ones vector is an eigenvector with eigenvalue 0. Okay. More difficult, showing that the second eigenvalue, if I have a connected graph, actually is not 0. So now, say G is connected. It's enough to show the following. If I have an eigenvector with eigenvalue 0, then it's actually just a scalar multiple of the one eigenvector that I already found. Remember the way that we sort of count multiplicity here? Yes, there's infinitely many eigenvectors that have eigenvalue 0 by taking scalar multiples of the all ones vector. But to have a second eigenvalue of 0, I would have to have a linearly independent vector from that also gives me an eigenvalue of 0. So I'm going to show that if G is connected and I have an eigenvector with eigenvalue 0, then it actually is just a multiple of the all ones vector. Okay, so how do I do that? I can certainly write down this. We've been looking at products like that a lot. If I take x times my Laplacian, I get 0. So of course, then if I dot the 0 vector with anything, including x transpose, I just get 0 as a number. But we saw that there's a nice formula for x transpose, sorry, not A, L. There's a nice formula for x transpose Lx, right? This is a sum, we first wrote it as a sum of x transpose LVIVJ x, but we saw that each of those terms in the sum are actually just this difference, the square of this difference between the ith and the jth entry of my vector x. Okay, and so actually I get something really strong from the fact that this sum is equal to 0. Every single term in that sum is either 0 or strictly positive, right? So if even one term in that sum is bigger than 0, then I don't have this whole sum equal to 0. So for every edge vi, vj, I must have xi equals xj. Now, there's plenty, in a connected graph, there could be plenty of vertices that don't have edges between them, but because G is connected, what's the definition? I always tell my students in graph theory, every time I ask you to prove that a graph is connected, I want you to say a graph is connected means that for any two vertices, I can find a path between them. So I'm going to show that I can find a path between them. Okay, I have a connected graph. The definition of being connected is that for any vi and vj not equal, okay, I guess even if they are equal, the trivial thing, but we'll think about vi and vj not being equal. There exists a vi vj path. Okay, so here I start at vi. I end at vj. Maybe this is a one-edge path. Maybe it's really long. I have an associated entry, xi of vi. I know this is an edge of the path. So whatever vertex this is, maybe it's, some vk, and it really corresponds to the kth entry of my eigenvector. But the kth entry and the ith entry are equal because this is an edge. So whatever the index of the entry is, its value is equal to xi. And now the value of this guy's entry in the vector is xi. And I just percolate down my path. So yes, that thing has a different entry in the vector that it corresponds to, but xj is equal to xi. So as soon as I fix a value for xi for one vector, or for one entry of my vector, one vertex, every single entry in my vector is equal to that xi. So this says there is some alpha where alpha times the all ones vector gives me this x. And that's what we need to show, right? So the eigen, what do they call it? The eigenspace or whatever. The set of eigenvectors with eigenvalue 0 is a one-dimensional subspace of Rn. And this probably, like I was saying, we're not going to sort of go more into depth on this, but this maybe already gives you some indication of like, if you had a disconnected graph, so you have components, you should be able to make a zero-valued eigenvector kind of by thinking about, okay, well, maybe I would fix all the vertices in one component have a non-zero entry in this eigenvector, and they would all have to be the same. But then I could have a different non-zero entry or 0 for all the vertices in a different component. So I think actually there's a statement that like if G has k components, then the multiplicity of 0 as an eigenvalue is exactly k plus, or exactly k. Okay, that does deserve QED. And now No, I still need a little bit there. No. I just shouldn't crumple this paper prematurely. Okay. So last topic, I have an hour, maybe-ish.
Whatever you need. I think we'll just go past 24 hours. Or I'll cut it. Yeah.
We'll make it work.
Yeah, I know. Okay, I know.
But don't feel put off. When you're done, you're done.
Okay, I think that this will work okay as far as timing. The last thing I'm going to do is something that, okay, the second to last thing I'm going to do is drink some more Red Bull. Sponsored.
By the way, that's approximately the halfway
Wow!
For the like anticipated end of 9 a.m. or 9 a.m.
mark. Right. I
Sunday
mean, it
next
may
day?
not be the minimum.
I mean, yeah, we could keep going forever. Okay, so the last thing that we're going to do involving the Laplacian, the reason I wanted to make sure that we talked about the Laplacian is Kirchhoff's matrix tree theorem. This is something that I wish I had seen earlier. It's a really, really cool theorem. If you've heard of Kirchhoff's matrix tree theorem before, it's potentially because it can be applied to give a fast proof of Cayley's tree formula, counting the number of spanning trees in a complete graph. But Kirchhoff's matrix tree theorem is actually a much more general statement that tells you something about how you can use the Laplacian of a graph to figure out exactly how many spanning trees the graph has. Okay, so in a graph G, a spanning tree is a subgraph T with the same vertex set as G. So it uses all the same vertices that G uses. And it's supposed to be a tree. A tree is just a connected graph that doesn't have any cycles in it. So I can even, draw like a fast example here. Maybe that's my graph. What does a spanning tree look like? Well, here's one. Right, I just sort of pick edges until I have things that connect everything everywhere, but I want to sort of be minimal about it. I don't want to have any cycles included. But clearly from this example, many graphs have more than one spanning tree. There can be spanning trees that overlap a little bit like that. If you have a really dense graph, maybe you can even find like edge disjoint spanning trees. There's probably interesting questions about decomposing cliques into spanning trees, how many ways you can do that. I'm being speculative here. But if you just have a random graph, how many spanning trees does it have? I'm going to consider spanning trees distinct. Like these are all labeled vertices. So even if I can find two isomorphic spanning trees, I'm going to consider those to be different. If they have, if even one edge is different, they're two different spanning trees. Given a random graph, how many total spanning trees does it have?
Cut an edge and delete an edge. Is that like T of the graph is equal to T of the graph. Take the edge out plus T of G. You know what I mean?
Like a recurrence relation?
Yeah.
Those with an edge, those not on that edge?
Actually, that is an observation that we're basically going to use in our proof. Yes, so there are ways that you can sort of think about figuring out how many spanning trees a graph has by thinking in some kind of recursive way of like making subgraphs or closely associated graphs and counting spanning trees in those. So there is going to be some sort of inductive way that we can figure out a formula for this. That said, the formula is going to look a little bit weird. And if you're getting bored, just like try, here's K5. You're going to be at it for a while. I know you can use Kaylee's. If you don't tell people what the number is. If you don't like my lecture, find all the spanning trees in there. Justify that you found exactly all of them and have not counted any more than once. Okay. So I have a slide here, which is going to introduce the last sort of linear algebra thing that I'm going to scamper lightly over, which is taking determinants of matrices. Probably all of us have taken the determinant of at least a 2x2 matrix. We know it has this formula, AD minus BC. The determinant is a slightly mysterious, maybe, property of a matrix. You, for bigger matrices, can take determinants in several sort of equivalent ways. For us, actually, the most useful way to think about defining the determinant of an n by n matrix is with this weird looking formula. So I'm thinking here about adding up products of the entries in my matrix, and I multiply each product of the entries that I add up by this sign of a permutation that's associated to the product. So a permutation of the numbers 1 through n just sort of shuffles them up. So according to a permutation that I choose, I'm going to have the entries that I pick out to multiply. They all are in, row 1, then row 2, then row 3, but the columns that they go into are determined by this permutation. Then the sign of a permutation is an abstract algebra thing associated with the permutation. It talks about how many transpositions you need to multiply together to express this permutation. So a transposition just swaps two elements exactly. And it's a fact that every permutation can be expressed as either the product of some odd number of transpositions or the product of some even number of transpositions, but not both. So sign is either 1 or -1, depending on whether you need an even or an odd number. So this looks really ugly, yes? But it turns out that thinking in this way is going to let us prove quickly a lemma that we'll need about how to think about determinants of big matrices without doing some explicit cofactor expansion. Okay, so I'll have that fact on the next slide. Determinant fact. And we're going to use this to prove Kirchhoff's matrix tree theorem. So what does this theorem say? If I have any n-vertex graph G at all, and I want to figure out how many labeled, meaning the names on the vertices matter, how many labeled spanning trees G has, what I do is I take my Laplacian, I pick any index that I want, I delete the ith row and ith column of the Laplacian, and then I take the determinant of that cofactor. Not only is this theorem saying that any ith row and ith column of the Laplacian that I delete, I will get the same determinant of that cofactor, but that determinant magically is always equal to exactly the number of spanning trees in the graph. This is a bananas theorem. This was, I don't know how you figure this out. And apparently this, I wrote a comment that was like, oh yeah, this Kirchhoff proved this before we had this and that piece of terminology that makes this easy to state in linear algebra terms. It's how? But that's the statement, and this is basically the last thing that we're going to prove. We'll use it to imply Cayley's tree formula at the end. Okay, so towards the Kirchhoff matrix tree theorem, I'm going to start with a lemma And the point of this lemma is going to sort of make it easier for me to understand these determinants that I'm taking. So here's a lemma. For an n by n real valued matrix A, I'm going to let EII be the matrix with 1 in entry II and zeros elsewhere. Then the determinant of A plus this EII is the same as taking the determinant just of A and then adding the determinant of this cofactor where I delete row and column I. By the way, I don't use linear algebra as much as I want to in my research, and so every time I see a statement like this, I'm like, how is it? It's insane that one, people figure these things out, and two, that they're true. Maybe not in that order. Okay, but like I said, the reason why I have that fact about the determinant, in a minute we're going to switch to a nicer way of thinking about determinants, but I have that fact about the determinant because thinking about determinants as these sums of permutation products times signs is going to make it much easier for us to see why these things should be equal. Okay, so as always, I like to just put hats on things when it's not exactly the matrix A. So I'll say that the entries of A plus EII are AIJ hat. I'll even say KJ hat because I is kind of a special fixed index here. Almost always these entries are the same as the entries of A. The only thing that adding this EII does is to one specific entry, it adds 1. Okay, so by this formula, if I want to take the determinant of A plus EII, I'm going to take this big sum over all of the permutations of 1 through n of A1 sigma of 1 hat through A hat n sigma of n. And these are being multiplied by the sign of my permutation. Okay, what we want to observe is that usually the things in this sum look exactly like the things that we add up to find the determinants of A. So if sigma of I is not equal to I, so I don't see a II hat in this product, then the term that I observe every single one of these A hats is just equal to the entry that it corresponds to in the matrix A. Something special happens if my permutation fixes the point I. So if sigma of I equals I, then I see sine of phi, sigma it's still the case that most of these entries, I can just erase the hat and they're equal to what that entry is in my matrix A. But to erase the hat from this sigma of I is just I, to erase the hat from that, I have to add 1. But having one term in this product where I add 1 really isn't too bad. If you think about what this product is doing, this is really the sign of my permutation, sigma, multiplied by all of the unhatted things. And then from this plus 1, I just get sine of sigma times everything in this product except the II term. So I get sine of sigma, A1 sigma of 1, A n sigma of n, no II term. And the key observation is, okay, if I add up all of the ones where I is not fixed by sigma, and sort of this first half of every term where I is fixed by sigma, I get exactly the determinant of my matrix A. So we just want to convince ourselves that if I add up for the ones where I is fixed by sigma, these slightly different products, where I have the sign of this sigma, and I have basically everything that sigma is permuting, but I've dropped the II term, then that's the same as the determinant of my ith cofactor. And that's basically true, because you can just think of the ith cofactor. Think about its rows and columns being indexed exactly the same. You've just erased entry I. Then the permutations of everything except I are the same as the permutations of everything, including I, that just sort of fix I and then erase I from there. And it's not hard to check that the signs of those permutations sort of don't change if you think about deleting I. Okay, so this is maybe slightly sketchy, but I'll still say QED. It's not, the interesting part, but I wanted to, justify when we use a fact that looks magical. We have this nice way that we can think about the determinants of our cofactors and original matrix being related. Okay, so I'm going to use that to prove the Kirchhoff matrix tree theorem. This is cool. It's a simultaneous induction. Or multiple induction, or I don't know what the technical term is for it, but I'm inducting sort of on two things at once. So let's start with like the smallest possible case really here. N equals 2, M equals 0. So my graph is two isolated vertices. Here my Laplacian is 0, 0, 0, 0. All LG I's are that tiny matrix. I don't need to do any linear algebra to say the determinant of that is 0. And there's no spanning trees because the graph is not connected, right? I can't walk from this vertex to that vertex. So if I ever have a disconnected graph, it has 0 spanning trees because a spanning tree is a connected subgraph, right? Trees sort of all glue together into just one component. So good job, base case. For the inductive step, I'm going to let G be a graph on n at least 2 vertices, m edges, and suppose the theorem holds for graphs on n minus 1 vertices and n vertex graphs with m minus 1 edges. So you can do this. I guess if you sort of think about how the induction builds up, next I would check like the 2 vertex 1 edge case, and then I graduate to 3 vertices. So like 3 vertices, 0 edges, then 3 vertices, 1 edge. And 3. So you can build up induction in this way, even though we don't usually think about induction as having sort of 2 variables that we're inducting on at once. Okay, so why is it important that I'm inducting on n and m simultaneously? Because we had this really good suggestion here that you could sort of think of spanning trees of a graph as corresponding to spanning trees in like some subgraph. For the rest of the proof, we're going to let tau of G be number of spanning trees in G. G minus E is subgraph obtained by just deleting the edge E. So take your graph, just erase an edge that you don't want to see anymore, and otherwise it's the same. And then there's going to be a second operation that we consider, which is the edge contraction operation. G mod E, I guess, is going to be the subgraph obtained by contracting edge E. To show you sort of a picture of what a contraction looks like, I want to sort of think about taking an edge and turning it into a vertex. Okay, I will allow, under this contraction operation, multiple edges. I won't leave a loop when I contract. So this turns into just a vertex that corresponds to E.
If you were contracting a multiple edge, would you leave a loop in that case or delete both edges?
Okay, good question. So the graph we start with is simple.
Right.
So I never contract something that was a multiple edge. I'm only going to do one contraction ever. Yeah. If we were doing multiple contractions, then yeah, you'd have to ask what it means to contract an edge if there's a multi-edge between the 2 vertices. In this case, we're only going to think about one contraction. So the weirdest it could look is if these guys have a common neighbor, we would have a multi-edge like that. And then I have any edges going out of E to anything that was a neighbor of one or the other side. Okay, so the observations that we want to make are basically about how spanning trees in G correspond to either spanning trees in G minus E or G contract E. So I think I'm actually just going to note this first. We're obviously going to have to erase some stuff before we get to the end. So I'm going to note how this deletion and contraction business works, and then we'll do the cases. If E is any edge of G that I want, every spanning tree of G either contains E or does not. Hopefully we believe that even at 9:30 at night. Trees containing E are actually in one-to-one correspondence with trees in G contract E. If I have a spanning tree, so imagine deleting everything in G until you get a spanning tree. If E is an edge in that tree, I can just slurp E down from an edge into a single vertex, and I get a tree still. Doing that contraction operation, if I don't have any cycles in my graph, won't create cycles. So I'll make a spanning tree of G contract E. And similarly, if I have a spanning tree of G contract E, I can unslurp the vertex corresponding to E into the edge E, and I'll make a spanning tree containing E in my original graph. So there's a one-to-one correspondence here. And similarly, even probably easier to see, trees avoiding E are in one-to-one correspondence with trees in G minus E. Right, a spanning tree of G that avoids the edge E is exactly the same as a spanning tree in G, just with the edge E deleted altogether. Okay. So actually, I can maybe erase my torture exercise here and just make a little boxed observation here. The number of spanning trees in G is exactly number of spanning trees in G contract E plus number of spanning trees in G minus E. And so how does this induction work? G contract E has fewer vertices, right? I've taken two vertices and slurped them together into one. G minus E has the same number of vertices but fewer edges. So since I'm inducting on both things simultaneously, I'm going to be able to apply induction to both of these graphs to say the number of spanning trees in this is going to be given by a determinant, number of spanning trees in that is going to be given by a determinant, and then I'll try to sort of add those determinants together and convince myself that I get the right thing when I do. Okay, so let's erase. We believe the base case. And now let's think about doing this inductive step. I'm actually going to break into two cases because I'm trying to prove something strong, that any cofactor I choose is going to give me the same determinant, and it's always going to be the right thing. What this is kind of going to correspond to is saying that I'm going to get the same answer by induction no matter what edge I pick in my graph. But to always get the same answer, I'm going to need to be able to pick edges that touch each vertex, and how the index of the vertex that my edge touches is going to correspond to what cofactor I look at. So what could go wrong? Well, what if the graph I'm looking at has an isolated vertex? So a vertex with degree 0 that no edges touch. If that's the case, then the sort of vague thing I said about wanting to, look at an edge touching this vertex and contract along that edge isn't going to work because there's no edges I can choose. But fortunately, if I have a graph containing an isolated vertex, it's not that hard to see that I'm going to get the right thing from my determinant formulas. Okay, so say VI. Then what's going to happen? My Laplacian has zeros in row and column I. right? Entries of row 1, column I. The II entry is the degree of vertex I. That's 0. The ij entries for j not equal to I say, is there an edge from I to j? Those are all going to give me zeros. So I have a 0 row and a 0 column. So let's think about sort of the two different ways that I could choose a cofactor and look at its determinant. If I delete this 0 row and 0 column, then actually because I is an isolated vertex that doesn't correspond to any of the non-zero entries in my Laplacian matrix, this cofactor is just the same as the Laplacian for G with VI deleted. Well, the thing I would be worried about, in general, it's not true that a cofactor like this is a smaller Laplacian, because when I delete a vertex from my graph, I could mess up like the degrees of other vertices, which would change the diagonal entries of the Laplacian of the deleted thing. But here, deleting VI does not change any entries in my matrix. It just sort of erases row and column VI. So I'm going to use another determinant fact, maybe a nicer way to think about determinants than this ugly sign permutation thing. The determinant of a matrix also happens to be the product of its eigenvalues. So if I know that I'm taking the determinant of a Laplacian, one of its eigenvalues at least is always 0. So I'm just going to get a determinant of 0 when I multiply them all together. And similarly, the determinant, if I delete a j row and column for j not equal to I, is going to be 0 because I maintain a row column of all zeros when I look at that cofactor. So you can, it's not hard in that case to like even explicitly construct an eigenvector that has eigenvalue 0. Okay, and in this case, these are exactly the things that I want because the number of entries in G is 0 anytime G is disconnected. So the number of spanning trees is 0. I have shown explicitly that all of these cofactor determinants are the same. They're all equal to 0, so I get the right thing. Case 2, no isolated vertices. So what I'm going to do now is fix any I that I want and think about some edge VI, Vj. There's no isolated vertices, so for any vertex Vi I choose, I can find an edge Vi, Vj. And we have seen that the number of spanning trees in G is the same as the number of spanning trees in G contract VI, Vj plus the number of spanning trees in G delete VI, Vj. So what I want to do is say I can apply induction to both of those smaller graphs. And then the last step is just going to be to play around with the determinants that I get a little bit and convince myself that I actually, when I add together the two things on the right, get the determinant of the ith cofactor. Da, 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 da. So the last step, relating determinants. I have a lemma that we proved a while back, and you might guess I'm going to want to use it pretty soon. So let's write some things down. Thinking about the ith cofactor here, I can say it's pretty close to this. The ith cofactor of the Laplacian of g minus e with one thing added. We talked about when I delete an edge e, what sort of things change. Well, the entries in the Laplacian that said edge e is there will change from -1 to 0. But those entries are both either in row I or column I. So the only other things that change are the two endpoints of e, their degrees drop by 1. The II entry I'm deleting when I take the ith cofactor anyway. The jj entry lives. And so here, it's sort of one smaller than it should be over here. So I'm going to add ejj back to fix that. So this tells me that the determinant of LGI is the same as the determinant of this sum, LG minus E, ith cofactor, plus EJJ. And this is supposed to be equal to sorry, one sec. Oh, yeah, no, here's where I use my lemma. I was like, that's not obvious. Well, it's not obvious because I'm applying the lemma. Okay, I have exactly the type of sum that I have this lemma to break apart. So this is the same as the determinant of the ith cofactor of g minus e, plus the determinant of, okay, so now this j kind of also gets deleted. So I get the determinant of LG minus e, ith cofactor, plus the determinant of LG minus e, delete row and column I and j. So I'm actually very close to being done here. I know this guy by induction, so what I want to say is that this guy is kind of the other cofactor determinant that I'm interested in. And LG minus E with I and j deleted is supposed to be the same as LG contract E with I deleted. So why is that true? I'm going to think about when I have VI and VJ kind of contracting VJ onto VI. So in G contract E, I have a vertex that corresponds to VI, but no vertex that corresponds to VJ. And then what's like the degree and edge information in this graph with the contractions? Well, the edge that E, the stuff that edge E did no longer exists, it's gone. But kind of the only differences that I see should be in, there's no longer a row and column I, j. There is a row and column I, but if I delete that, then all of the degree and edge information for vertices that weren't either of the contracted vertices is the same. right? The degrees of vertices that are not equal to I or j don't change. If they were adjacent to I and or j, they still are. And the edges that don't involve vi or vj don't change. Okay. So this is in fact equal to taking the determinant of the ith cofactor of g minus e. Now, that's not great board work. It all kind of is blending together. I take the determinant of L g minus e, delete I, plus the determinant of L g contract e, delete I. And by induction, I get exactly spanning trees in G minus E plus spanning trees in G contract E. QED. Okay, very last thing to do. Would be to think about the most famous case of trying to count spanning trees, and that's in the complete graph. So if you've heard about Cayley's matrix tree, or Cayley's tree formula, you might not have heard this phrased exactly this way in terms of spanning trees, but a labeled spanning tree of Kn is just the same as like a labeled tree on n vertices. So this is the number of ways that we can make a spanning tree in an n vertex complete graph, or if you like, the number of ways that I can make a tree on n vertices, which are labeled so they're distinct. And the n minus 2, very, very pretty. There are plenty of non-spectral graph theory proofs of this, but it does follow really fast from the matrix tree theorem. So Cayley's tree formula says we should get n to the n minus 2. The matrix tree theorem says write down the Laplacian of Kn, delete any row column you want, and find what the determinant of that is. One way that you can figure out the determinant is by finding the eigenvalues and multiplying them all together. Equivalently, I have there, you can show that this determinant always should be the eigenvalues of your original Laplacian with the 0 eigenvalue dropped, divided by n. Okay, so let's write out what Laplacian we actually get. I have on the diagonal the degrees of everything, which will be n minus 1 for every vertex in a clique. On the off diagonal, I have -1 if there's an edge between two vertices, and 0 if not. The clique, every two vertices have an edge between them. So I just see that. Now, for example, I can just delete row 1 and column 1. Any row or column I choose, I'm going to get the same cofactor when I delete. But as we saw from Kirchhoff's matrix tree theorem, even if you get distinct cofactors, you'll always get the same determinant. Okay, so for instance, I do this. So now I have n minus 1 rows and columns here instead of n. That's going to be important. For one thing, this is going to stop me from having a 0 eigenvalue. The 0 eigenvalue really kind of followed from the fact that for any row, the row sum was 0. Now the row sums and column sums are not 0. So if you're saying, oh, this looks exactly like the Laplacian that you had, and Laplacians have 0 eigenvalues, so shouldn't the determinant always be 0? The fact that we have deleted things actually is changing stuff about what my eigenvalues will be. Okay, so what are my eigenvectors going to look like? Well, again, I kind of think it's fun to just get your hands dirty and actually write out what the sort of equation would be and solve the system explicitly. So here I have n minus 1, dot, dot, dot. I'm multiplying by v1, v2 through vn minus 1. And this is supposed to equal lambda times v1, v2 through vn minus 1. Okay, so for each I get n minus 1 times vi. When I take the ith row here, I'll have n minus 1 times vi minus the sum of vj for j not equal to I. And this is equal to lambda times vi. I can actually rewrite this to make it look a little bit nicer. My minus 1 times vi, I could kind of slurp into all of this to just be thinking of subtracting every single entry of my eigenvector. So rewriting, I could add that all over to the other side. Add up all of the entries, subtract lambda vi from both sides. I'm going to get n minus lambda times vi. Okay, and that holds for every single entry. The right-hand side is always the same number, no matter what I fix. So this says either the entries in my eigenvector add up to 0, and this is a coefficient of 0, or if that doesn't happen, then I can kind of divide by this coefficient, and I can conclude that every single element in my vector is the same. So either every vi is the same, or lambda, or n minus lambda is 0, so lambda equals n. If every element is the same, I can assume they're all 1. Then what happens? N minus 1, or n minus 1. When I multiply here now, I get n minus 1, and then I subtract n minus 2 copies, not n minus 1 copies. So n minus 1 minus n minus 2 everywhere. I just get the all ones vector back. So I don't have a 0 eigenvalue anymore. I have an eigenvalue of 1. With multiplicity, only 1, right? We just said that the span of this vector is the only type of vector that's going to do that. I have to have all entries equal to have an eigenvalue of 1. That means, okay, this is an n minus 1 by n minus 1 matrix. It's going to have n minus 2 other eigenvalues counting multiplicity. They all have to be n. So determinant of this Laplacian cofactor is, again, determinant fact, product of eigenvalues, 1 times n to the n minus 2. $17. Thanks. Thanks.